Now, that was the hard way. There was a lot of work in there, okay? But I wonder if it twigged with you as we were going through, particularly around here when we were doing this integral, and these things cancelled out. You ought to be really suspicious of the answer, right? It's very simple, okay? How could we have seen it from here without doing this whole translation and forming new integrals and that kind of thing, okay? Well, if your graph is any good, come back to the first time you graphed this question, okay? Now, where are 4/5 and pi on this diagram, right? Well, 4/5 is this width here and this width here, right? And pi is, where's pi? Pi is the height of the whole graph, right? Can you see it? Can you see it yet?
Oh my god.
4/5 wide. Pi radians high. It's just a rectangle, okay? So what's the easy way? Here's the easy way. Now, I'll admit, it would be nice if I could just write down the equations, but see what I just did there, okay? Unfortunately, or maybe fortunately, you don't get to go to the marker and get a whiteboard out and draw this and then color it in and say, ta-da. Okay, so we need to provide something verbal that explains what I just did, okay? So here's what I would suggest. On your diagram, you must have a diagram, okay? Do some labeling. I've got 3 areas here, okay, which I'm interested in, okay? I can say on the definition, right, this integral is equal to those 2 bottom areas, okay, because they are the areas underneath the curve, okay? So I haven't made any dramatic statements here, okay? But then I can say, and you should have some more space here to actually write this, but I'm just going to go on to the next line. From the graph, because you actually do need to have a graph drawn to make this argument, okay? From the graph, I can say that these 2 areas are equivalent, right? Assuming your graph is good enough, right? A2 equals A3. On what principle are they equivalent? And the answer is symmetry, right? It's not an even function or an odd function, but if you rotate it around this point, 0 pi on 2, okay? You'll get A2 becoming A3 just by rotating it around, okay? So I would say bisymmetry.
So you're saying bisymmetry now?
I'm sort of doing both of these, right? So if I didn't have the graph, I can't argue bisymmetry, right? But having got a graph where it's clear, yes I can, okay? So therefore, the integral is equal to A1 plus A3, which is a rectangle, which is that wide and that high. And that's the evaluation, okay? So should you do it the easy way or the hard way? Assuming you can spot it, right? Clearly the easy way is better, though you can't make any of the arguments without the graph. You must have a graph, okay? You can't simply go from here to here, right? Here. Even if you only say this is not enough if you don't have some kind of illustration. Yeah.
If the question's like that and it's like that long working out, but it's only like 1 or 2 marks, does that usually mean there's always
So yeah, people will see. I'd expect this would be this would be the question, and I expect it to have 2 marks. And many people will start doing it the normal way that you do one of these kinds of areas, and they'll be like, well, they'll either realize something is wrong. Okay, but might not work out that they can do this trick. Maybe because their graph is. I remember the first time I looked at a question like this, my cos inverse curve was so off. I literally could not see the symmetry because it wasn't symmetrical on my diagram, right? So if you don't spot it, you're like, oh, okay, I'll get here eventually. But yeah, you're still going to get the same 2 marks. And you're like, that was a lot of work because you didn't realize there was a quicker way. I did still want to show you that though, because this is useful, this is instructive, this identity. Okay, just to go back to where Daniel suggested it, it's also a good point. You do cos inverse, which looks like that, right? And minus cos inverse is the same thing but flipped, right? So you think about addition of ordinates, right? You've got pi plus 0, which is pi, a point like this, you've got pi on 2 plus pi on 2, which is pi. You've got 0 plus pi on 2 again. And then at every point, you think about how this is decreasing, and this is increasing at the same rate. So that's why you're going to get a straight line, namely y equals pi. Okay? So that argument also works. But I wanted to show you that you can use the methods we've been doing already, the algebraic methods, to show the identity. Yeah?
Can we use that identity like without proving it?
You mean this?
Yes.
Yep. Just like you can use, say, sine squared plus cos squared equals 1. It comes out of the fact that it comes out of all of these facts, actually. So, yeah. There are other ones like that, right? For instance, without actually proving it, I wonder how many of you could tell me, could guess what this is equal to. Think about it. It's very, very similar to this, but not quite. What's the difference between sine inverse of x and cos inverse of minus x? What's the difference? Do you remember when we were looking at integration, we looked at the difference? Yeah, there's a shift. It's a constant, right? So
it should be equal to pi on 2.
yeah, that's right. Sine inverse of x is cos inverse of minus x brought down pi on 2 units. Okay, so seeing as the whole thing is brought down pi on 2, you expect it should be pi on 2 less than this, which is pi on 2. Okay, you can verify by differentiating as well, because you know what these two derivatives are, it's constant, then you evaluate a value.